Hi there, AP Calc gang. Here's the last lesson in Chapter 6 on population growth. We'll cover a couple different models, one that you've seen before and one that'll be brand new. Again, this is not particularly a calculus topic, but there are some differential equations in here which applies to calculus, of course. First one, as you can see here, is the exponential model. We saw this last lesson. We've used it a little bit. Here we are slightly different in that we're talking about populations instead of just strictly exponential growth. But the idea here is that it's unlimited growth. As you can see by this graph, the population keeps rising. If it was exponential decay, the population would keep declining. So here's that equation that we saw before. Here's the p sub 0, the initial amount. Here's E. Here's that constant k along with the time. Now here's the differential equation. If I take the derivative of this, I would end up with something like that, k times the population, and if I wanted to even solve for k, I would further divide by the big population p here. This k value in this particular setting is called the relative population growth, and so that's what that's all about. Now we're going to look at an example here and see what we can deal with as far as that goes. Now here's Mankato currently has a population of about 53,000. That is with both Mankato and North Mankato with a relative growth rate of 13%. That seems really high to me, but that's according to this particular website anyway. We would like to write a differential equation for that, find a formula for that population in terms of t, and then use that formula to predict Mankato's population in the year 2020. So I think you'll find this will be fairly straightforward here. First of all, just got to change my pen color here a bit. The differential equation is just going to be that easy one, which is dp over dt, and that's going to be k times p. We already know what that k value is, so we just write it like that. Now the actual population will look like this. We do know what the initial one is. That's at 53,000. And then we multiply that by e to the kt. We know already what k is, so I can write that right in there like that. So there is my population right there. And when I'm trying to estimate what Mankato's population then will be in the year 2020, I simply take 53,000 like that times e raised to the 0.13, and then I multiply that by 7 because of course 2020 is 7 years from right now. Now when I do that, I get this fairly large number of 131,669. Now that seems rather large for Mankato, more than doubling in 7 years. Not impossible, but highly unlikely. And therein lies the trouble with exponential growth, is that it does keep growing, even though various economic or environmental issues would prevent that from happening in all likelihood. So here's the other one we're going to take a look at, the logistic model. This should be brand new to you, probably don't know much about that. And the advantage of the logistic model is that there is a maximum population that will occur. We call that the carrying capacity. A lot of times that's used when we talk about populations of animals in certain spots, and we'll see an example of that. Now, here's the actual logistic model right here. This M is that carrying capacity. Oftentimes the problem will tell you what that is, and over 1 plus A times, here's my E to the negative KT in this case again. This A value is something we'll try to figure out. So this is the equation for the population. Here is the population for the derivative. Notice it's got the K in there, the population, also that M, and the carrying capacity. This one is just rearranging that a little bit. Oftentimes they'll give you the differential equation in this form. You'll have to maybe pick out some of the key things in it. Alright, so here's my favorite animal, gorillas. So a problem related to that. So we know that this carrying capacity of this Rwandan preserve is 250. They had 28 in 1970. Here is the actual rate. Now notice this is the calculus part, the differential equation here, hi Puma. And we want to try to find a formula for the gorilla population and then predict how long it would take to reach that carrying capacity. Alright, so first thing I'm going to do is see if I can figure out what that K value is. Now right here, if you look on your last slide here, this was actually K over M. And so, second here. So if I know that this 0.004 is K, I guess I need another 0 in there too, don't I? 0.0004 is K over M, and I know that the M value I can tell from the other part of that equation is 250. Well, I should be able to just multiply 250 times that 0.0004. Sure enough, I do get that K is 0.1. Alright, so that means that I can go and try to figure out now my population equation. So it is going to be 250, that's that big M, over 1 plus A times E to the negative 0.1 T. So my first job here is to try to solve that for A. Now, essentially we can put a 0 in for T, because even though it is 1970, since it is our initial population, that is the P sub 0 basically. And so this is 1 plus A, and it's going to be E to the 0 because of that time equal to 0. Now, what do you know about anything to the 0 power? Is just equal to 1. So we really just have 1 plus A in that denominator there. So if I rearrange things here now a little bit, I'll then get that 28 times 1 plus A is equal to 250. I can divide both sides by 28 right away, and so then I'll get 1 plus A equals 250 over 28, and eventually then A is going to be, if I figure this out, about 7.9. That's kind of rounding it for the sake of our videos here. So what I'm looking for then for this equation will look something like this. The P of T equals 250, that's my carrying capacity, remember, over 1 plus 7.9 times e to the negative 0.1 t, like that. That's my equation. Next, I would like to take a look and see if I could figure out how long it's going to take for that gorilla population in 1970 to actually reach that carrying capacity. So I'm going to set up my same equation that I had before. Now, I'm going to put in not the carrying capacity, but just a little bit less than that, because if I did put in the exact number, some stuff would go haywire in my equation. So I want to put in something that's really close but not exactly equal to 250. I'm going to use that same A value that I figured out, and this is going to be e to the negative 0.1 t, like that. Okay, so now my job is really to figure out what t is. And if you remember a little bit from last lesson, the way to get at that exponent like that is to use some logarithms. We'll be doing that here in a second. So I think you can see that, well, to try to solve this, I'd probably multiply both sides by this denominator right here. So what I'm going to end up with then is 249.5 times that 1 plus 7.9 e to the negative 0.1 t, like that. And that should equal 250. I'm going to omit some steps here because it'll take up too much room. Ultimately, what I'm going to end up with after I distribute this 249.5 and do a little subtracting and all that kind of stuff, I'm going to ultimately end up with e to that negative 0.1t equaling about 0.0002, and I skipped a bunch of steps in there, but we can figure these out. Now, how do I get at that? Well, once again, I'm going to take that ln of each side here, and what that will enable to happen is this exponent then will move out in front. And that ln of e we remember that that's always equal to 1. And so basically, what I'll have then is I'll have this negative 0.1t equaling the ln of 0.002. So if I divide both sides by that negative 0.1 like this, then my answer is that t is going to end up to be about 82.8. And it's going to take that many years for that gorilla population to level off. All right, so that is the deal there. So thanks for watching, everybody, and we'll see you guys in class.